All right, guys, we are going to hop into vodcast 8.4. We're going to talk about percent yield. And again, this is still in the stoichiometry unit, so we're still going to be using stoichiometric principles of using balanced equations, doing some mole ratios, all that stuff. It's going to tie back into our last section of limiting reactants as well. So let me pop something up here on the screen that is probably going to horrify you a little bit. By no means, please don't copy this down or anything like that. This is a big, giant, massive, basically this is called the Haber process, okay? And what this is this whole thing, and again, you don't have to copy notes on this, but this whole process is one of the most important processes in industrial chemistry. This is how ammonia gets produced. If you look down here, like at the very end, we have liquid ammonia. The reason that ammonia is so important, like, you might be thinking to yourself, like, why is ammonia so important? I mean, yes, it's a cleaning product, but who cares? Ammonia is so important because it's like the precursor chemical, the chemical that you use to make almost all industrial fertilizer. That's part one of why it's so important. Part two of why it's so important is it's chemical number one that goes into the production of almost all explosives in the world also. And so between World War I and World War II, they really wanted to get a lot more ammonia, both for fertilizer, okay, because you need it to grow crops, and we've got 7 billion people to feed on the planet now. But at that time, they needed the fertilizer, and they also needed explosives. They were sort of gearing up in the interwar period for World War II. And particularly in Germany, this was really important. The Allies, the British and the Americans and the French and all them, they had access to saltpeter deposits in Chile, and those are largely ammonium-based compounds, and that's what they use for fertilizer. But the Germans were sort of cut off from this stuff, and so they needed some other way to generate ammonia, both for fertilizer and for explosives. So they came up with this big, long process here that I'm not really going to go through, but it's called the Haber process. And I said all that to say that we do all these calculations in chemistry class saying that I'm going to get so many grams of this out or whatever, as though every time I did this, it automatically came out perfectly and I got 100% of everything. But that's not what happens in the real world. And throughout them doing this Haber process, they did not end up with 100%, even with this big, complicated process. In a lot of cases, you might get 40% or 60%. And if you had a chemical process that you came out to be 90%, you would be really happy. So in the real world, we never get 100%. And please don't copy this page either. But there are a lot of reasons why we wouldn't get 100%. And just sort of know what a couple of these are. I mean, if you feel like you want to copy a couple of them down, that's okay. But there are lots of reasons why. If we were doing this, the Haber process even, some of the stuff would leak out. Some of the reactants might leak out. Some of the products might leak out, particularly if they're gases. Now, this doesn't happen as much anymore because we have really tight industrial controls, but always a possibility. And certainly if we're working on stuff in the lab, you might get a little bit of that. A lot of times the stuff that you're starting with, the reactants, are not 100% pure. Okay? So if you're not 100% pure, then your calculations are going to be a little inaccurate. You're not going to get the maximum amount of product out. Sometimes the product is lost when it's purified, so you get the product at the end, and then you have to go through a bunch of stages to purify it. Pharmaceuticals are a really good example of this, that you might produce aspirin like we do at the end of the year in AP class, but what you get is not pure aspirin, and so you've got to treat it a few times until you get just that product, and you're going to lose some of the product in the process. Sometimes the reactions work in reverse. That's really common. Sometimes the products react really quickly to form other things. There are side reactions. Sometimes you may get 100% or might have, but it just happens so slowly that it's not useful to you. Okay, so all of those are reasons why we need this, which is called percent yield. Percent yield basically tells us how much did you get compared to what you thought you were going to get. Okay, if you got everything that you thought at the end, then you would get 100% yield, but usually you get lower than that. Okay, so terms. Actual yield is what you actually get. Okay, so like if you're doing this in the lab, when you weigh your final product, that's the actual yield. And we're going to do a lab here, if not tomorrow, in the next few days, where we're going to get an actual yield. And what you weigh at the end, that's what you actually got. Okay, that's in a problem, it's going to say that is how much is actually produced. Usually this is the number that's given to you in the problem. The second definition is theoretical yield. Theoretical yield is what you should get, okay, or the maximum value that you could possibly have gotten if everything worked out perfectly, okay? That's the 100% mark, okay? So to find the percent, you take the actual, you divide it by the theoretical, and then you multiply it by 100 to turn it into a percent. Now, sometimes they're both given to you in the problem, okay? So let's see one of those. So let's look at this problem. What's the percent yield if the quantity of reactants is sufficient? In other words, they don't tell you how much reactants are, okay, but they give you two other numbers that are both products, okay? Cl2O is a product. So it's sufficient to produce 0.86 grams. In other words, this number is my theoretical yield. How do I know that? Because it says it's sufficient to produce 0.86 grams, okay? It could. If everything was perfect, it would produce 0.86 grams. But, okay, only 0.71 grams is obtained. If you see is obtained or is produced or was measured, those are all indicators of actual yield. So this then is my actual yield, okay? So what does that mean for us calculation-wise? Well, calculation-wise, my formula says that I put actual yield, okay, over theoretical yield, all right, and then I multiply them by 100%. Now, when I punch this into the calculator, I'm going to get 82.558, blah, 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 a bunch of numbers after that. I'm going to round that to 2 sig figs. Both of my things that I start with have 2 sig figs, and so that turns out to be 83%. And actually, that's a pretty good percent yield. Like if we were working something in the lab and you got 83% yield, that's pretty good. Again, a lot of industrial processes, you're lucky if you get, 40% sometimes, which seems kind of wasteful, but I mean, that's really the way it works a lot of times. So I get 83%. Again, actual yield says is obtained, is produced, you measured, was found in the lab. Theoretical yield sometimes is given to you, and it'll say something like this: sufficient to produce, or optimally produces, or could produce. Those are all theoreticals. The way it usually works, though, is that the theoretical is not given to you. Pretty much every problem you get, the actual is going to be given to you, but very often the theoretical is not given, okay? And how do you know that the theoretical is not given to you? Here's how it works. So if 72.0 grams of C2H2, that's acetylene, reacts with excess bromine and 720 grams of the product, we're going to call this the product because that's a long formula, is recovered, what is the percent yield? Okay, so here's the deal. It says 729 grams of the product is recovered. Okay, automatically I know that that is my actual yield. Okay, so that's good news. That's one thing that I don't have to calculate. Oh my gosh, why can I not write AY? Actual yield. Okay, sorry about that. My pen skills are apparently falling apart. Okay, so that's actual yield. So the other number that's given, if you look at this, first off, this says 729 grams of the product. It has to be a product. If I look at this one, C2H2, acetylene, not a product. It's a reactant. If you're given a reactant, here's what it means. It means that this is not the theoretical yield. Okay, first off, it couldn't be the theoretical yield. If I divided 729 by 72 and then multiplied it by 100, I would get 1,000%, and you would be an awesome sorceress magician if you got 1,000%. Like, I put this in and I got more out. Doesn't work that way, okay? So that's your first clue. Your second clue is it's a reactant. If you have a reactant, you have to do stoichiometry, okay? And that amount of reactant is my given. Now remember, the reason I'm doing stoichiometry is to find the theoretical yield, okay? So the theoretical yield should be my unknown, and my theoretical yield has to be the same as whatever my actual yield is. Not the number, but it has to be the same thing, okay? And the same thing in this case is the product, which is this stuff. There's only one product, so that's the product. So what am I looking for? I'm looking for grams of that stuff, okay? Which is, let's see, 1122 dibromomethane. Yeah, something like that. Gosh, I'm sure I'm botching that up somehow because I didn't draw the structure out. But anyway, this is where I'm actually going to abbreviate this because that's a lot for you guys to write. I'm just going to call that the product. Okay? So I got a stoichiometry problem here, and this is what's going to determine my theoretical yield. And when I get it, I'm going to plug it back in to find the percent yield. Okay? So anytime I'm working gram to gram stoichiometry, I need three things. I need the mole ratio, which in this case is 1 mole of acetylene, that's my given, equals 1 mole of CHBr2, okay? So 1 to 1 mole ratio, and then I need the molar mass of each thing, okay? So calculate your molar mass, and you can pause and calculate those out if you want. My molar mass of acetylene is 26 grams equals 1 mole. Okay. My molar mass of this big honking thing that we're going to call the product. Okay, and in fact, I think I'm just going to call it that. 1 mole of the product is equal to, in this case, it's equal to 345.6 grams, okay, of product, okay, or CHBr2, all right? And once I've got all three things, then I know that I can go from grams to grams. That's what all of my stoichiometric problems are. So I've got bunches of conversion factors here, okay, 3, because you got 1 conversion factor for each of these. So I start off with my given, 72.0 grams of acetylene. I want to get rid of that first, so I'm going to put 26 grams of acetylene. And again, this is just straight up stoichiometry that we did in unit 8.2, okay, a couple of sections ago in this unit that you've done probably copious amounts of problems on in class at this point. So this is nothing really fancy here that we're doing. We've been doing this. Don't let this part scare you. This is the easy part of the problem. Actually, I mean, this is really the long part of the problem. Okay, so 1 mole of the product. Remember, I'm going to reduce all of this and just call it the product, or X or something like that, just to make it a little bit easier. And 1 mole of product, and then grams of the product. And yes, I know at some point some other chemistry teacher is going to look at this and say, I can't believe you didn't write the whole thing out. I know. I should have. But I'd run out of space here, and my writing is bad enough as it is. And why torture my kids more than I have to with my terrible writing? So I'm going to cancel what cancels. Grams of acetylene cancel. Moles of acetylene cancels. Moles of products cancel. Now, guys, one thing I want to talk about real quick is when you're doing this, don't just run through and cancel stuff. Make sure it actually cancels. Grams with grams. Moles with moles. Moles with moles. If you're not checking this, there's really no point in setting this up. You're going to mess it all up anyway. Okay, so you got to check all that. Anyway, when I calculate all that, when I round it to sig figs, I get 957 grams of the product. Now, what is that? What does that represent? Okay, that is my theoretical yield. It's not my final answer. It's not my percent yield, but it's my theoretical. So what do I do with that? Okay, I then take my actual yield that, remember, is back in the problem. Okay, 729 grams. I divide it by the theoretical that I just calculated. Okay, and then multiply it by 100. And when I punch that out, I'm going to get 76.2%. I'm going to keep 3 sig figs here because I had 3 in each of these things. Really, with percent yield, I don't worry as much about sig figs. I usually at least keep 1 decimal place. But that's it. Now, that is a lot of stuff and a lot of thinking. Okay? So what are the steps? So let's walk through the steps real quick. Step 1 is to determine what your actual yield is, and then what you need to find. If you have the theoretical, go ahead and calculate it. If you don't, like we did in this problem, determine how much of the reactant you have. Okay, that becomes your given. Your unknown then is whatever your actual yield is. So if your actual is in grams of some chemical, your unknown has to be grams of that same chemical. Okay. Then do stoichiometry. So find your equalities, okay, your mole ratio, your 2 molar masses, set up your railroad tracks, do your calculation. When you get your calculation, that is the theoretical yield. Okay, and then take your theoretical, take your actual from the problem, and plug them into the percent yield formula. All right, a lot of stuff there, but if, as with almost everything that we've done so far, if you do it step by step, be patient with it, you'll be all right. All right.